Our dear Senior 6 students, I welcome you all at Light Academy Secondary School e-learning platform. My name is Teacher Sevira Jime. Let me hope you are all okay. I'm going to take you through Senior 6 Mathematics Paper 2. And our topic today is linear interpolation and extrapolation. I'll start with linear interpolation. This is the process for finding the values of a function for intermediate values of the independent variables. Linear interpolation is based on the assumption that the limit function changes at constant rate for tabular values y1 and y2. Suppose a function f of x is given for equal spaced values of x, which lie in the range x1 less or equal to x less or equal to xn. We shall have our x values and function values f of x. When here we are having x1, we shall talk of function value f of x1. Then when we go to x2, function value will be f of x2, and so on up to xn, and the function value will be fxn. The process of linear interpolation seeks to find a value f of c for a non-tabulated value c, which lies inside the range. Remember, we had x1, the starting value, and xn, the last value. Now, the x value we are to find should be a value which is within that range. General equation of linear interpolation. That general equation of linear interpolation comes from this graph. Suppose we have a curve f of x, that curve having x values a with its corresponding function value f of a, another value c with its corresponding function value f of c, and finally the last value b with its corresponding function value f of b. Now here we use linear interpolation to find any value which is in between, so long as its corresponding x value is given and is within. Now, suppose a is given with its corresponding function value f of a, then b given with its corresponding value f of b, and now in case I give you a x value c and I ask you to find the corresponding function value f of c, now here we can employ linear interpolation to get that f of c. How? This curve f of x at the beginning is supposed to be approximated to be a straight line. Now, when I approximate it to be a straight line, that means I'll create two similar triangles, that is ABE and ACE. Those are the two similar triangles. Now, after having those two similar triangles, I will now equate the sides and divide. This is what I'm going to do. I'll say the height of a small triangle divided by the height of a big triangle is equal to the base of a small triangle divided by the base of the big triangle. I will divide them like this. BF divided by CE is equal to AB over AC. In simple terms, I'm now saying change in y divided by change in x is equal to change in y divided by change in x. In our O-level mathematics, we call that one gradient. Whenever you see that I'm writing change in y divided by change in x, that means I'm considering gradients. Consider the graph of a function shown above. Suppose fx is given for some values x equal to a and x equal to b. Then we can use the linear interpolation to find f of c for a value c which lies in the range a and b. That means in case I give you a and b with their corresponding functional values, and then I ask you to find another functional value of c in case I give you c, that means you can use gradients to get that value c. In doing so, a curve fx is approximated to a straight line. I think I've mentioned that. Using triangles ABF and SCE, which are similar. I think I've already explained this. FB divided by EC is equal to AB divided by SC. Now, this one is the Y, the change in Y. This one is the change in X. This one is change in Y. This is change in X. That is FC minus FA divided by C minus A is equal to FB minus FA over B minus A. That is, I can get what is here, bring it down here, and what is here, take it up, because I can cross multiply. From the above equation, we can make FC the subject of the formula. Remember, our unknown was f of c, this one, f of c. That's why I'm talking of making f of c from this equation. Therefore, f of c becomes c minus a over b minus a into f of b minus f of a close plus f of a. And this is what we call linear interpolation equation. Let us see our first example. The table below shows the values of f of x for given values of x. We have x, f of x, 0.2, functional value 0.307, 0.4, functional value 0.506, functional value 0.6, 0.712, functional value 0.8, 0.891. Now, use the linear interpolation to find Roman 1, f of 0.5. Roman 2, the value of x for which f of x is equal to 0.670. Now, here, Roman 1, we are talking of f of 0.2. That means this one is sitting in the position of x because we talk of f of x. If this is sitting in the position of x, we shall first locate where 0.5 lies among the x values. And now here you can see 0.5 can't be in between 0.1 and 0.4. And you agree with me, 0.5 is in between 0.4 and 0.6. That means we shall locate it and put it in between 0.4 and 0.6. Let us see our solution. Now I copied this table from the main table in the question. Now in that I can easily show you where we are going to put our x value. Now our x value is in between 0.4 and 0.6. That's why I had to extract out another table from that one, x f of x, 0.4, 0.5, because 0.5 is in between 0.4 and 0.6. Then write the corresponding function value of 0.4, which is 0.506, 0.5, that is f of c, 0.6, that is 0.712. Now, f of c is the unknown, is what we are supposed to get. Now, what we are going to do, we are going to use the gradient method. We've already seen it from above, from that previous slide, that change in y divided by change in x is equal to change in y divided by change in x. You just need to be consistent. Now, here we are going to do this. This minus this over this minus this is equal to this value minus this value over this value minus this value. But another person can decide to subtract like this. This minus this, that is also change in y, over this minus this, that's also change in x, is equal to this minus this all over that minus that. That's also change in x. Remember, the negatives will come, and since you have a negative up and a negative down, they will cancel and then come up with the same answer. Now let us see what we are to do. F of c, that is the functional value, minus 0.506 over 0.5 minus 0.4 is equal to 0.712 minus 0.506 all over 0.6 minus 0.5 is what I've written here. That is change in y over change in x is equal to change in y over change in x. When you simplify that and make f of c the subject, you're going to come up with the answer 0.609. Let's go to Roman 2. Now I extracted this same table, the one we are having in the question. Now we are supposed to get the x value corresponding to f of x equal to 0.670. Now on locating that value among the functional value, is in between 0.506 and 0.712. That means we shall draw a table also having those two and then fit in the middle value. That's why now here the middle value is this one, and then I had to put here unknown. Now here we are going to say change in y over change in x is equal to change in y over change in x, which is 0.670 minus 0.506 over a minus 0.5 is equal to 0.712 minus 0.506 over 0.6 minus 0.4, which is this. When you try to simplify this and make a the subject, you'll be in position to get the unknown a. But we have another option, or now here I said a minus 0.4 over 0.670 minus 0.506 is equal to 0.6 minus 0.4 over 0.712 minus 0.506. Now here, down here we are saying change in y over change in, change in x over change in y is equal to change in x over change in y. Likewise, the other side I told you, in case we take the reciprocal, that means we've not changed it. Take the reciprocal on the left, take the reciprocal on the right, the two arms will remain equal. Now let us advance to linear extrapolation. In the same way, linear extrapolation is similar to that one of linear interpolation, but the only difference, now this time the unknown value is outside the range, is not in the middle, is outside the range. That's why you're hearing the word extrapolation, extra. That means it's not within, it's outside. That means we shall be knowing the x value a with the corresponding functional value, the x value b with the corresponding functional value, then we are given a value c and we are told to find its corresponding functional value. In the same way, we are just going to also approximate this curve to be a straight line and also consider a triangle ABC to be similar to ACE and also equate gradients. Consider the graph above, just like in linear interpolation. Here we have just dislocated C. I think I've demonstrated that, i.e. this time C lies outside the range. A and C. C is on the extreme end, it's not in between like in linear interpolation. For both linear interpolation and linear extrapolation, equations we use gradients of line segments of AB and BC. That for both cases we use gradients of line segments. That is f of c minus f of b over c minus b is equal to f of b minus f of a over b minus a. That is also gradient. Example 1. Given a table of a function t and d, we have 0, 0, 2, 4.1, 4, 5.8, 6, 6.7, 8, 7.5. Use linear extrapolation to find d when t is 9.5, t when d is 9.2, d when t is 7.2. Now, to justify that here we are dealing with extra, you can see among the t values, this one is going to be located at the extreme, just after 8. That is this side, that means it's extra. This 9.2 among the d values is also bigger than this. That means it's also extra. But this t 7.2 is in between this and this. Okay, we shall see how to deal with that. Let us see our solution. We shall start with locating our first value of t is 9.2 and it's at the extreme. That means we shall consider this value, and then put one other value, which is the unknown, which is this. Now our unknown is at the extreme end. Now we shall say change in y, which is a minus 6.7 over 9.7 minus 6 is equal to 7.5 minus 6.7 over 8 minus 6, and then when you make a the subject, you come up with 8.1. Roman 2. I'll extract the same table and then located also B. Now B, the value, the t value corresponding to 9.2, the d value is also at the extreme this side. In the same way, we start with the gradient. But here I said, let us always endeavor to start with the unknown. That's why here I'm now using change in x. B minus 6 over 9.2 minus 6.7 is equal to 8 minus 6 over 7.5 minus 6.7. When you make B the subject, you come up with B equal to 12.25. Roman 3. Now, here is a different story. Our 7.2 is not at the extreme, but is in the middle. Now, what we are going to do, we are just going to pick this value and fit it here. But since we are using extrapolation, we are not going to consider the last value. I will take 4, 6, and 7.2. And then put the unknown below there. Now, here, if you consider this, you see that C is really extra. It's at the extreme end. And then use our normal gradient and then get C. C minus 5.8 over 7.2 minus 4 is equal to 6.7 minus 5.8 over 6 minus 8. When you solve that, you come up with C equal to 7.24. Exercise. Let me give you some means and you copy that exercise down and you try it out. Let me hope you've completed the first question. Let us go to the second question. Let me hope you've done with the second question. Now let us advance to the third. Let me hope you've completed putting down those three questions. In our presentation, we've seen how to use linear interpolation and linear extrapolation, and we said interpolation is used when the value we want to find is in the middle, is an intermediate value, and we've just said that we are supposed to equate gradients. Change in y over change in x is equal to change in y over change in x for both cases. That is linear interpolation and linear extrapolation. Thank you for listening. In our next presentation, we shall be looking at roots of the equations of the form f(x) equal to 0. Thank you for listening.